second part, Jorge will talk about some challenges which are coming in the near future and some research linked to these challenges. So first of all, a brief introduction. I think that most of you know these things, but I just want to get everyone on the same page. So we are talking about real-time software here. Real-time software is software where time matters, which means that failure to respond is as bad as getting a wrong response. And that means that in our flight software, we have timing requirements coming from the system requirements, GNC requirements, from hardware-software interaction analysis. And these requirements are then translated into design and implementation issues such as tasks, latencies, jitters, and all these things which we need to deal with when performing what we call the schedulability analysis. And so these timing issues are then verified through analysis and testing, and I would primarily focus today on the analysis part. When we talk about hard real-time, then having hard real-time system means that we have deadlines which are hard, which must be met at all times. And so you can see it in a way that there is some time value function which returns 1 if the deadline is met, and any time before the deadline, but after the deadline the value is 0. It has no value for us. And this does not mean, or it does not imply what the criticality of the missed deadline is. In hard real-time system, the way you analyze the world is more or less black and white. You need to ensure that deadlines are met. You don't analyze what exactly happens if they are not met. On the other hand, in soft real-time systems, the deadlines are kind of more approximate, and you end up analyzing the system by measuring what is the likelihood of meeting deadlines, how far away from deadlines the tasks are, and you end up doing some probabilistic methods which are fairly complicated, and that's why sometimes you can hear people stating that hard real-time is hard, but soft real-time is actually harder. But in the end, having no deadline at all is actually better than having hard deadlines, of course. And then it is possible in a single system to mix hard real-time and soft real-time tasks. It's a little bit error-prone because of resources which are shared between those tasks, and therefore the analysis of this system could be a little bit more complicated. And now I come to what we do at ESA. At ESA, how we see flight software is as hard real-time system. That means we don't analyze consequence of overruns. Simply we make all possible, all needed to make sure that there are no overruns. So I think that certainly we can identify some tasks which, in case they don't meet a deadline, the consequence is not that critical, but in most cases we simply don't do it because it's simpler to analyze the system as purely hard real-time system. Otherwise we would have to have some robustness analysis to study what exactly happens if this or that task does not meet its deadline. Although I must mention that recently we see that in some projects there is tendency to introduce tasks with no deadlines or soft deadlines, but the analysis is not there yet. It's not fully adjusted to this model. And this is an overview of software development process as we do it at ESA, and with its phases and milestones. And I want to say just briefly that in terms of timing properties and schedulability analysis, we come from the system requirements, then we have some specific software timing requirements and possibly some design constraints, such as design constraint could be which operating system should be used or which type of scheduling should be used. And then in the design phase, we have a very important thing which is called computational model, which is part of dynamic design. I will get back to this on the next slide. And we already define in preliminary schedulability analysis document what is the way to analyze this system. And then during the production phase, we, well, iteratively, as long as more code is finalized, we replace in our preliminary technical budget, we replace estimates by real measurements, and we also do associated schedulability analysis, which becomes final at the time of validation testing, together with some verification and validation report. And the same is when we verify with respect to the system requirements. And related to the dynamic design and computational model, the dynamic design should describe what the behavior of the system is in terms of describing all tasks, how they are activated, what are the events which activate them, or whether they are scheduled based on time constraints or by processor clock. And then the important part, which is the computational model part, is to define what the tasks can and cannot do. And then there are many other things, such as task communication means, interrupts, type of scheduling. I should say that we still, in some systems to be launched, some missions use the cyclic static scheduler, although more and more we used preemptive scheduling. And then some other things, how tasks are synchronized, how resources are protected, and then some distribution aspects and communication aspects. An important observation is, or an important statement, that the weaker the computational model is, that means if you allow your tasks to do many things, and they have too big freedom, then the schedulability analysis is getting quite complicated. And the same is with design. If the design is not detailed enough, then again, the schedulability analysis is affected by this. In terms of the analysis itself, we use the standard rate monotonic analysis, sometimes with blocking involved as well. So that's the analysis based on how processor is loaded. But more and more we use response time analysis and also some proprietary models such as tasks with offsets, and we also used something called adjusted multi-frame model in one case. And then we end up with a table of tasks, which is a standard task table, like something like this. This is an example of such a table with all tasks listed and their properties such as frequency, deadline, worst case execution time, blocking, utilization, that means how much of processor time they use, and possibly response time if the method is response time analysis. So all the resources are taken into account, or interrupt handlers, or all system overheads, such as preemption latency, interrupt latency, and these kind of things. For the schedulability analysis, it's important to say that we use so-called operational scenarios. That means that we consider realistic traffic on telemetry and telecommands, realistic operations, which are different for different modes, and we use so-called heavy stress scenario to use the worst case load in order to prove that the system is schedulable. We see some challenges in the current approach, and most of the challenges are linked to the fact that there is several sources of pessimism in the analysis method itself. So already in the requirements, we have things like telecommand upload rate, which means that we have to budget our system to make sure that this telecommand upload rate, which is typically defined per second or per unit of time, is possible to make in every unit, in every second. However, it's typically not that bad in an average load. The same is with architectural and detail design. We see that lack of detail causes problems with the analysis. And one example is what I already mentioned, which is that we consider all tasks as hard real time. And then in particular, for preemptive systems, we can see that the analysis itself is very much pessimistic because it combines worst case scenarios in a single scenario with very small likelihood that this worst case scenario can actually ever happen. We consider worst case preemption rates for all tasks. We consider worst case blocking for all tasks. The assumption is that all semaphores are always locked for every activation of a task. Of course, not if some particular protocols like priority ceiling are used, or if we go into more detailed analysis and see whether actually these resources are used by individual tasks or not. But that's not the mainstream response time analysis which you normally do. So often what we can see in, for instance, Earth observation satellites, that if we have maximum load defined as 75% of the processor usage, that means there is 25% should not be used. In fact, what we see is that the nominal load is about 20 to 25%, and although we can prove that the system is barely schedulable, the reality seems to be different. It's only the analysis which makes it feel that the load is so bad. So our observation is that if the use of preemptive systems is very nice because you can delay certain timing aspects to later, because your tasks are not that much fixed to specific time slot as it is in cyclic scheduling, which is very good and very convenient, but it is convenient only as long as the system is schedulable. If you end up in a situation that you cannot prove that the system is schedulable, then all these nice features and worst case assumptions suddenly are not good enough, and you have to get into more complicated analysis. And of course, one of the other challenges is that the hardware we use is not as fast as we would like it to be, but that has been always the case. But especially if you compare to some other domains, the processors are rather slow. And then it's worth mentioning that in terms of tools which we use for schedulability analysis and also worst case execution time measurements, there is no unified set of tools in different ESA projects. And the reason for that is that ESA cannot impose usage of particular tools in different projects, but also that the scheduling methods in all these projects are always just enough different from the mainstream so that we seem to be unable to use these tools. And for worst case execution time measurements tools and the tools which are based on some estimates, there we regard them as providing too high and pessimistic numbers so that we cannot use them. So often we resort with some ad hoc methods like using spreadsheets for schedulability analysis. I leave floor for Jorge.
So, good afternoon. Can everyone hear me? Yeah. So, I'm going to talk a little bit about what is the approach that ESA is taking for some of the challenges we are going to be facing in the near future. So, well, like everybody else, ESA has been looking into cache, into a way to minimize the impact on cache performance. And on the on-two compressor, there is an about 2.5 performance improvement if we use CAS in a typical onboard software application without any specific CAS optimization. And this is a big improvement, but as we have discussed several times today, if we use CAS, then we will have less predictability, and this will make it harder to analyze the WC. But what make CAS harder to analyze? What make CAS non-deterministic? Well, several things. Things like the memory layout and use will minimize or maximize the CAS conflict, or task preemption, where the effect is very dependent on the actual point preemption. The problem here is also that this effect will actually arise on a state of mind in a very complex way. So ESA has been doing a lot of research for the last year, and we have been working in cache-aware cellular. We have been working on several things like make the cache only available for one core, or make the cache only available for one partition or one specific task. And we have been also working on modifying linker script in order to generate different binaries with different memory layout that will minimize the cache conflict. So, multicore. Multicore has been researched for many years as well, and ESA has been looking into this as well. And well, the first thing is that there is no direct correlation between the classical schedulability approach we have been using single core to multicore. What I mean with this is that on single core, we can simplify and say that it's relatively easy to measure the WC, then apply some margin, then we use a fixed priority preemption scheduler, and we will know that the tasks are going to meet their deadline. But on multicore is not that easy. Why not? Well, first, because it's difficult to get a tight and safe WC estimation. And this is because of inter-task interferences. This is something that we have seen the whole day. When we are running several applications, several tasks on multi-core, on parallel, they are all sharing the same hardware resources. Floating point unit, L2CAS, memory. So if we hit the case where more than one task needs to access the same hardware resource at the same time, then an arbitration state will be required. And this, of course, has an impact on the WC, and that is really bad because the WC depends on the workload. So this is really bad. However, if we can obtain a 0% performance degradation if we schedule on different core non-interfering tasks. So in this sense, task scheduling is going to be a key player in the future of multi-core if we want to reduce inter-task interferences. And even dynamic scheduling, where priorities can be modified at runtime, like PDF or similar, will actually lead us to a higher CPU utilization. And these ideas are very, very nice, but are nice for soft runtime and for low difficulty tasks. But we all know that for hard runtime, where missing a deadline is just not acceptable, is something that we cannot do. So, can we split between soft runtime and hard runtime? Well, if we use logical partition with a strong spatial and temporal isolation, this will allow us to co-hosting application with different difficulty levels on the same platform. On an integrated, non-partitioned image, an error in one application could propagate to the rest of the application running on the onboard software. This practically means that for all the applications running on the same platform, we have to develop according to the same criticality level. And this results on an additional effort if you want to maintain system safety. Time space partitioning will allow application with different criticality level to be allocated to a specific partition, ensuring verification or validation of the application on the actual criticality level. So we will maintain system safety with this idea. And for us, we think that time and space partitioning and multi-core is a logical and powerful combination. We were talking last some case, if you use FTIR partition, in some case, fixed cyclic cellular does not allow for accumulation on error conditions. So with tiny space partitioning or multi-core, we can actually choose a different scheduling policy per core. This is a really nice idea because, for example, we can use 3-core with using a fixed cyclic scheduling, and then 1 core using a dynamic scheduling where we can execute the interrupt handler, we can execute the FTIR partition, or we can execute some low criticality partition between interrupts. Well, model-driven software engineering is another thing everybody else has been looking for some time. It's a new programming model where non-functional properties related to timing, like control flow, deadlines, communication budget, and concurrency properties must become an integral part of a software component description. And this allows us developing TASTE, which is a GPL tool that allows us to model the architecture, and it has connection with Schedule, so it provides automatically schedulability analysis. And as I say, it's a new programming model where you forget about number of tasks you want to use, you forget about method, you forget about everything. You just define some timing property in some software component, like you can do right now with the application programming interface, and then you let the tool to automatically generate a proven by design model of the architecture. This looks amazing on paper, looks really nice, looks like it's going to make our life easier, but so far we don't have experience from real project. We want to start using this on real project as well, and then we will see if there are any further limitations on this actually that we can really use. So, in conclusion, this is an overall description of what is the ESA approach together with the European space industry to unify what is the current approach for the challenges we are facing right now in the schedulability analysis, and what is the whole ESA is looking at the future with scheduling on multi-core, which for us is still a research topic, for us is still open, but we expect that time and space partitioning could actually make it easier, could actually split architecture in several pieces, and this could make easier to analyze. And from model-driven engineering, that, as I say, on paper right now looks really nice, but from a stability point of view, this is still an open issue for us in a real project, and this is something we want to use. All these things that ESA is researching has not only an impact on the software, but also on the hardware with some modifications as we have seen in the previous Aerospace presentation. And I think that's about it. So thank you very much for listening. And if you have any questions, feel free to ask.
No questions.
Do you know how much more efficient your processing? You'd mentioned in there something about you can have, I guess, more processing power, so to speak, less latency or less dead time. Do you have any idea how much that might improve if everything was working as fast?
I don't know. That will depend, because if we go to multi-core, we have this problem with the hardware, that at the end we are sharing the same hardware resources, so you have a limitation of the floating point, the task that can actually access to the floating point unit at the same time, and this kind of thing. So I don't know.
The number 20 to 25% margin, or I'm sorry, not the margin,
Yeah.
but I saw on the slides 20 to 25% nominal CPU
Yeah.
load. Is that taken from an average of actual missions, or is it just the observation?
I must say, I did not say that, but it's not that I would have done an exhaustive research
Right.
on all missions, but I have seen several cases where this is what we see, that the load is actually very, very low on the processor, although on paper, if we try to provide mathematical proof that the system is schedulable, it looks like really, really loaded, full speed. But I think the point is, well, of course, we have to account for worst cases, for burst of telecommands and this sort of things. But I think it's more the analysis method which pushes us a little bit into the corner and then gives us maybe more freedom in the design that we have preemption and we just define tasks and they do what they do and we assign priorities and it's very easy to design such a system, but then as a result we don't use efficiently the CPU power we have.
How do you validate your analysis and how often do you revisit the analysis?
Well, the analysis, there's not a single one, so it's always developed for a particular mission and well, peer reviews and so multiple people look at it and but pretty much it's often something which you can find in the books plus with some minor modifications, so it's not that difficult to see that the method itself is sound. Plus then you have to trust the measurements and this sort of stuff, and then you get into things like worst case execution times and whether they are good enough and this sort of stuff. Anyone else?
No one else has anything?